Okay, this is example 5 in your book on page 64. So the question here is, what happens when your given differential equation is neither separable, nor linear, nor homogeneous? What do we do then? And this is where, again, Bernoulli's equation comes in very, very handy. This actually is, we are going to have a Bernoulli equation. Okay, and if you don't see it in the beginning, that's okay. We're going to, again, transform this. So this is our differential equation. And again, I want to write this Bernoulli equation because it's going to be helpful when you're taking your test. I'm sure you'll probably have it on your cheat sheet, which I encourage you to. Q of xy to the n. Okay, so remember that if n, in this case, if n is 0 or if n is 1, then this Bernoulli equation becomes linear. And then we can use find our rho of x, our integrating factor, and go from there. So remember, on your exam, you want to determine if it's separable, is it linear? Can't do linearity. Is it homogeneous? And if it's not homogeneous, it's probably a Bernoulli equation. So if we rewrite this, we can definitely divide. Okay, so we can do this, right? Again, the reason I'm doing this is because I want it to look like this form. So we get dy, so we're technically here, dy dx plus 6 over xy equals 3y to the 4/3. And notice there is our p of x, right, just directly, and here is our q of x. Right? Just happens to be a constant. Technically, you can write 3x to the 0. That's still 3 since x to the 0 is 1. Okay, so this is very good news because it is a Bernoulli equation. But here I want you to notice our n, right? Very important n. Okay, our n here is 4/3. Okay, so it's not 0 or 1. So we can't use the integrating factor. Okay, that's fine. We just, we rule that out. We're going to solve this differential equation by not using the integrating factor. So let's write a couple things down. Okay, so we have our p of x, our q of x, we have our n. And so now let's start, all right, let us start the substitution method, right, that we learned in 1.6. And again, on your cheat sheet, on your test, I hope you have again this Bernoulli equation. And I would probably, I wrote in the other video, I let v be a certain y, and then after that everything's pretty easy. So I'm going to let v, according to Bernoulli, it's always going to be y to the 1 minus n. Well, our n in this case is 4/3. Okay, that's just 3/3 minus 4/3, so we get y to the negative 1/3. Okay, so that's what our y equals, or what our v equals. So there's one relationship we're going to use. And then easily, if you solve for v here, or solve for y, right, I can raise this to the negative 3rd power, so then I just get v to the negative 3. Again, the goal is we want to rewrite this in terms of our v. Okay, so there's two relationships, and finally we are going to differentiate this guy, and so that's just going to be our dy dx. So dy dx, right? I'm really doing, again, d dx of y, which is dy dx. But remember, we're going to use, right, there's a chain rule here implied. because our v is really y to the negative 1/3. It's not just v. So remember, again, dy dx is just dv, just kidding, dy dv times dv dx, right? Notice, I mean, those are going to cancel anyway, so technically they're the same. So we have dy dx. Okay, what is our dy dv? Well, that's when you take the derivative of this guy, and that is going to be, according just to calculus, negative 3v to the negative 4 times, and then of course the chain rule, so that's dv dx. Okay, so that's what our dy dx is. So again, I'm going to not circle, but box our third relationship. Okay, so we have v, we have y, and we have dy dx. So this is a good little kind of summary. This is your thinking box. So you're solving for, right, you want a v equals, you want a y equals, and then you want a dy dx equals, okay, when you do the substitution, if that helps, or if it doesn't help, you don't have to write it down. Okay, so now we're ready to transform our differential equation of x and y into some, right, g of x and v. So let's move that up. Okay, so we have, I'm using, again, this is my x and y, right? This guy, right, that's my f of x and y, right? And again, I want to transform this equation into some, hopefully, g of x v, right, by substitution. Okay, so, well, dy dx, I have a dy dx right here. So we have negative 3v to the negative 4th times dv dx, right? That's my dy dx, plus 6 over x times y. Okay, well, what was our y? I just use a different color here. My y was right here, was v to the negative 3 equals 3, and again, y, which we know is just v to the negative 3, but we are raising that guy to the 4/3, and let me erase this line here, to the 4/3. Okay, so I substituted everything, I believe, yep, everything was the same. Actually, this one was the same. Okay, so let's just simplify this guy a little bit, not too bad. Okay, so I'm going to rewrite this again. Okay, plus 6v to the negative 3 over x equals, right, using our law of exponent rules from Algebra 1, we simply have a 3v to the negative 4. Again, I'm using, you know, x to the mn is x to the m times n. Okay. So now that you have transformed, right, your differential equation to a function of x and v by substitution, now you kind of go back and, right, you analyze this differential equation and you ask yourself, okay, now that it's in this form, is it linear? Is it separable maybe? Is it homogeneous? And in this case, it's actually going to be, well, from your book, I mean, it's going to be a linear first order differential equation. And again, I would have your definition of your first order linear differential equation on your cheat sheet, because that's going to help you set this up. So I'm just going to divide everything by negative 3v to the negative 4th, and you'll see why. And again, this is a practice. If you're wondering, you know, why am I doing this? Well, I've taught this many times that after a while it just comes naturally, but the more you practice, the more you see what you want it to look like, what the form is. So I want my dv dx, right, to be isolated, so right, it's just a big 1. So dv dx, plus, and again, I'm just using algebra. And we obtain, actually, this should be, here's my eraser. Eraser function's not working again. Okay. This should be, okay, so that's a division symbol. That should be minus, after you do the algebra, you get 2 over x, v equals, and then of course this guy is exactly the same, numerator over denominator, so that's just negative 1, and that should be a negative right there. Again, I'm just using law of exponents. If you're not sure, go to YouTube, Google law of exponents, and they'll give you a wonderful review. Okay, so this differential equation is linear. How do we know it's linear? Well, here's definitely our, whoops, our p of x, and this guy is q of x, but more importantly, right, this is our Bernoulli equation, but remember, when you have a Bernoulli equation, if n is 0 or n equals 1, then you know it's linear. Well, where's our n in this case? Well, this is really times, y to the 0, right? Because that, again, this is really just a big 1, right? Y to the 0 is 1. So this is, since n is equal to 0, then this Bernoulli equation is definitely linear, okay? It's linear, so that implies we can definitely use our integrating factor, rho of x, right? E to the integral p of x, okay, if it fits dx. Okay, so let's go ahead and do that. Okay, so let's calculate our rho of x. So rho of x is equal to E. And I'm integrating p of x, but I know I can definitely take out a constant. That's 1 over x dx. And let's work vertically here. E to the, this is going to be nice, ln of x. And I know my power, again, is going to be on top. And this is wonderful, because then we get rho of x. And if we multiply both sides by our rho of x, all right, which we've done many times, and hopefully you've had some practice from the previous homework, then we're going to get some kind of skipping some steps here, but hopefully you should be able to fill that in by now. If not, then let me know. So after multiplying again by rho of x, right, you're going to notice that the differential equation on the left-hand side is really this guy. Right, remember that's always going to be the rho of x. And then we're going to just simply get negative 1 over x squared. And then we have our little integrating party here. So integral with respect to dx. And this is gone, which is great. And then this is really, right, this is just negative x to the negative 2. So we get negative, let's see, x to the, well, if we add 1, we get x to the negative 1 plus our constant of integration. And discontinuing, all right, we get, you can write it like this if you'd like. Actually, might as well change it to a, this is really 1 over x minus c plus c. It's some arbitrary constant. Whoops. I wanted to move that up. That's still a c. Okay, so again, we're solving for y. And multiplying both sides by x to the negative 2, right? Because we want to isolate v, right? We simply get x plus c, again, x squared, or just c. And we know v is y to the negative 1/3, right? And almost done here. That's squared. We want to solve for y, or y of x. So I'm going to multiply both sides by, we're going to raise it to the 3rd power. So x plus c x squared, all actually to the negative 3rd power. And then finally, this is just using algebra. That's cubed. All right, that is the solution.